Today, most shoulder arthroplasty surgeons use some form of preoperative planning software. Today we will discuss BluePrint for shoulder arthroplasty, a look behind the curtain. By now, I think most of us understand that this type of software packages will provide the surgeon with a three-dimensional representation of the geometry of the glenohumeral joint for one particular patient, but also allow the surgeon to virtually place the components where they will provide the best possible reconstruction for each individual shoulder. As these programs have evolved, they have incorporated more features and now they form its own ecosystem. In the case of BluePrint, there is a number of planning features that go beyond the simple automatic analysis of the glenohumeral joint and include AI predictive analytic features for prediction of primordial anatomy or estimation of what would be best for a given patient in terms of anatomic or reverse arthroplasty. Also features for auto-planning, estimation of range of motion free of impingement in the case of reverse, and also virtual removal of bone, mostly osteophytes, to optimize range of motion. But today, these packages also provide execution solutions, including PSI guides, patient-specific base plates, navigation, and of course, Mako-robotic surgery. Let's talk a little bit about automatic glenohumeral analysis. When I go to different meetings and I hear people talking about this topic, I hear a couple of misconceptions. Number one, some surgeons say, well, pre-op planning seems to overestimate deformity when compared to 2D. And the key is to understand that when we were measuring deformity only on 2D images, like CT scans, for example, we were measuring differently. So yes, you will get different numbers if you measure on 2D versus 3D, not because one or the other is right or wrong, but because they are measuring differently. And the same is true with different vendors. Some surgeons say, if I input the CT scan of my patient into different vendors, I'm going to get different numbers, so someone must be wrong. But that's not true either. Each vendor has a proprietary algorithm that will give the surgeon different values depending on the vendor used. That is why it's so important to understand whatever program you use as a surgeon, how does it actually work? And I think it's important to understand what is the magic behind the curtain for BluePrint. So when you upload the CT scan of your patient into BluePrint, what's happening mathematically? What is the computation? And what happens is that all these different slices of the DICOM files of the CT scan are analyzed automatically, first to understand what is the boundary of cortical bone, so that different slices can be stacked and create a three-dimensional representation of the scapula. Then BluePrint will throw a number of points, a cloud, that will allow to compute what would be the plane that best fits the vertical aspect of the body of the scapula. And that will be your first reference point. Next, BluePrint will automatically identify in multiple slices where is the intersection between the body of the scapula and the spine of the scapula. And by connecting those different dots at the intersection between the scapular spine and the scapular body, we can then trace what we will call the transverse scapular axis. And then we're going to place a number of points on the surface of the glenoid that will allow to estimate the center of gravity. If we then allow BluePrint to place a best fitting sphere, that sphere will have a center itself, and the connection between the center of gravity of the glenoid and the center of the sphere is a vector that can then be used to estimate version and inclination. If we look straight from superiorly, whatever angle can be measured between the transverse scapular axis and the vector that connects the center of gravity of the glenoid with the center of the best fitting sphere is your version. If we look at the scapula straight from anteriorly, the angle between the transverse scapular axis and that vector that again connects the center of gravity of the glenoid with the center of the sphere will be your inclination, superior or inferior. Finally, BluePrint will estimate the best fitting sphere for the humeral head, and whatever volume of head is posterior to the best fitting vertical plane will give you your subluxation, anterior or posterior. Finally, BluePrint will estimate the center of the humeral head that will be used to estimate globalization, as we will discuss later on. So to summarize the steps one more time, first step, identify the best fitting vertical scapular plane. Next, identify the transversal scapular axis. Then identify the center of gravity of the glenoid and the center of the best fitting sphere to estimate version and inclination. Next, after establishing a coordinate system, understand where is the best fitting sphere of the humeral head to understand subluxation, and eventually where does the geometric center of the humeral head move after reconstruction. One question that's important to answer is, well, if we upload the CT scan of normal people into BluePrint, what values will we get? We did this. This is a study where we took CT scans of completely normal shoulders and we uploaded them on CT scan. And what we found is that on average, the human shoulder has 6 degrees of retroversion as measured by BluePrint. It can range between 3 of anteversion to 16 of retroversion. Regarding inclination, the mean inclination in this study was almost 8 degrees, but it ranged from 3 inferior to 21 superior. So for me, when I plan anatomic and reverse, my starting point is typically 5 to 6 degrees of retroversion because that is what's normal when you measure normal CT scans into BluePrint. Now let's talk about predictive analytics, a very fascinating field of artificial intelligence. There are a number of features that you can use in BluePrint to lever AI. Number one, you can understand if it's better for a given shoulder to consider anatomic and reverse. But the devil is in the details. There is a little box that you can see in the presentation, and if you click on it, it will explain to you that the way this tool was created is by using the plans of 9 expert surgeons. So in this case, what BluePrint is telling you is that there is a 56% chance that 9 experts would choose reverse for this particular patient. Automatic line prediction is very powerful. If you provide some reference points to BluePrint, you will be offered as a surgeon a plan that already is very close to what you would do based on your goals. And this is really revolutionary. We have now a tool that using statistical shape fitting can predict the premorbid anatomy for each shoulder. You can see here the shoulder with some osteophytes and some bone loss, and we can overlay easily the 3D rendering of the statistical shape fitting to understand where was the glenoid bone before erosion actually happened or before formation of osteophytes. There are some key numbers that are important to understand in BluePrint, but it's also important to understand that, at least for me, numbers do not only by themselves dictate what to do in terms of anatomic or reverse. I always plan. What's important is to understand what are the numbers that we use for prediction of range of motion free of impingement. There is the misconception that these numbers will predict the patient's motion after surgery, and that's not it. The only thing that this is doing is identifying where are the potential points of conflict between the polyethylene and the bone or between bone and bone so that we can optimize range of motion free of impingement. And finally, very important, glenoid lateralization in this program is measured as the distance between the surface of the glenoid bone and the base of the base plate, as you can see here. So in this example, on the right, I placed a lateralized glenosphere. But as you can see, the measurement of BluePrint is going to be identical and will not take into account glenosphere lateralization. Important to understand. Finally, how do we measure global lateralization and distalization? On the image on your left, you can see how BluePrint has identified as the green dot the lowest portion of the still intact glenoid, and on the purple point, the geometric center of the humeral head pre-reverse. If we now translate that into a reverse configuration, you can see now the more bright green spot is the new center of the humeral head. So the yellow lines tell you where did the purple point move to the bright green point distally and laterally, and that is your global lateralization and global distalization, but it's dramatically affected by the state of the shoulder before reconstruction. These two reverse arthroplasties are identical. You can see how the new location of the geometric center of rotation of the humeral head is at the same level. However, if the patient on the left had calf arthropathy with an E3 glenoid, preoperatively, in the morbid condition, that purple dot was very high and very medial. So when you make the calculation, people will tell you you are lateralizing and distalizing a fair amount. But you're reaching the same spot as the image on the right, and if the image on the right corresponds to a patient that has a massive catheter without arthropathy. You can see how the purple dot stays in the same level in terms of lateralization and is just distalized. So in summary, I think it's important to understand that these tools have really empowered surgeons to be much better in terms of planning and executing our arthroplasties, but it's also important to understand all the features that today, as a surgeon, you can get from this ecosystem, not only just understanding the glenohumeral joint geometry, but also applying contemporary artificial intelligence tools that can help you with predictive analytics, with estimation of range of motion, fear of impingement, and with which bone removal. And furthermore, if you're interested, you can use this tool to create your guides or your base plates or use Mako robotic surgery. Thank you very much for your attention.